All right, now we're at the Fundamental Theorem of Calculus Part 2. This is one of my favorite theorems because it's super useful and it kind of gets rid of us having to find those areas by hand, which is probably at this point getting pretty annoying. So, Fundamental Theorem of Calculus Part 2 says if we've got our continuous function over our interval, and then f of x is any antiderivative of our function, then that definite integral from a to b is equal to capital F of b minus capital F of a. So basically, if we find any one of our antiderivatives and plug in b, plug in a, and subtract them, we're going to get the area under our curve, which is really kind of weird to think about that's being true, that having to use those geometric formulas has been working, but this is going to give us a way to find area under any curve as long as we can find one of those antiderivatives. Now, what's great about, again, going back to part one guaranteed that if an integral exists, we could find it. So if it's integrable, we can get that antiderivative. And that's kind of sort of true, but we can do this. Sometimes it's a little too hard for us to find exactly, but for a lot of the things that we're going to look at, we're actually going to be able to find those antiderivatives. So kind of thinking about what we know about these definite integrals at this point. So we've got the integral from a to b of f of x dx. We know we can use those geometric formulas. We also know that this is equal to the limit as n goes into infinity of the sum of I equals 1 to n of, again, some height of each of our rectangles times the width of each of our rectangles. So again, this is saying that if we take one of those Riemann sums and take more and more rectangles, make them smaller and smaller and smaller, we'll get closer and closer to what that area is. And what this limit will actually approach is f of b minus f of a, where capital F is the antiderivative. I really don't want to be able to spell antiderivative. There we go. Antiderivative of that function little f of x. Or we can say that f prime of x, oops, I want to say it the other way. That capital f of x prime is equal to little f of x, which is what we had from the Fundamental Theorem of Calculus Part 1. So let's take one that we know that we can pretty easily find the antiderivative one that we can pretty easily look and figure out what our area is under this curve. So we've got our function here, and oops, and I want it to be the highlighter. There we go. And we can do our area under the curve. It's a triangle. We've done many examples like this before. So if we use geometry, so we'll put equal with geometry. This is equal to 1/2 times our base, which is 3 units. Yeah, 1, 2, 3. And our height, which is 6 units. And that's going to be 1/2 times 18, which is 9. Now, if we use the Fundamental Theorem of Calculus, we want to find our antiderivative. So the antiderivative of x is 1/2 x squared. So that 2 that's out in front, it hangs out. And we get our antiderivative of 1/2 x squared. And then 2x is the antiderivative of 2. Now, something that we do notation-wise so that we remember that we're finding a definite integral and not just an antiderivative is we'll put a little line after our antiderivative and then put our limits of integration. So this is just kind of split up this step here, that we've got this first part here where we're finding the antiderivative. And then the second part here is really mostly a reminder that we need to find the area. So this is a reminder to find the area so that we don't think that we're done once we've just found that antiderivative. So what do we get? We've got 2 times 1/2, that's just going to be x squared plus 2x. That's our antiderivative. And so we're going to do f of b which is 2, minus f of a, which is 1. So again, I'm being kind of overly dramatic about plugging these numbers in so that it's really clear about what we're doing here. And what do we get? We get 4 plus 4 minus 1 minus 2, so we're going to get 8 minus negative 1, which is 9, which is exactly what we got with our area formula, so we got the same thing. So this is telling us that if we can find that antiderivative, then we can find the area under our curve. So how this is going to be extremely helpful to us now is that now we can take functions that are like this, 1/2 e to the x, and we can find the area under this curve from 0 to natural log of 2. Because we know the antiderivative of e to the x. E to the x is its own derivative, so going backwards, we get e to the x. So that 1/2 gets to, again, just kind of hang out because it's a constant or a coefficient. It's not that it's a constant, it's because it's a coefficient. And then we put that line there to, again, to remind us we've got still more to do. We put our limits of integration on there. And then we're going to do our f of b minus f of a. So we're going to plug in natural log of 2 and plug in 0. And let's see, e to the natural log of 2 is 2, because the e and the natural log do cancel out. And then minus 1/2 times 1. So we're going to get 1 minus 1/2. So we're going to get 1/2 is our area under our curve. So no more rectangles, no more trying to find, things that are shapes. We can find the area under any curve as long as we can get that antiderivative.